Okay, welcome to this problem solving session. Here I'll be solving a problem on axial forces, stress and strain. So, from chapter 2 of the Mechanics of Materials text. So in this problem, it says for the steel truss 200 gigapascal, that's the Young's modulus and loading shown, determine the deformation of members AB and AD, knowing that their cross-sectional areas are 2,400 millimeters squared and 18,000 millimeters, 1,800 millimeters squared, respectively. So for the problem here, it says determine the deformation. So deformation, it's what we mean here. It's like it's deflection, right? I mean that's delta PL over AE. Now for this problem, if force is applied here, right? Of course, we expect certain movements to happen in this part. In this part, there should be some form of, deformation. Here is fixed, but here there's a roller, right? So that means that it can move y and z. Y and x, right, basically. So for this problem now, we need, it says, okay, so determine the deformation of members AB, that's the deformation AB, and deformation AD. Now this is AB here, and this is AD here. So now for this we need to find these components, but then of course we have to find the forces associated with that, basically the forces associated with this. So for that, let's begin. Now in looking at this problem, we have a force being applied at this end here. That's at this point, right? Of course, for this structure to be in equilibrium, that force will be countered by a force here and a force here too. So, right. So let's assume let's represent this truss, this line. So let's represent this truss with these lines, assuming this force acts at the center here, 228 kilonewton. For it to be countered by these two forces, they must be equal, right? We can see from here that this is 4 millimeters. Here it's also 4 millimeters as well, right? So let's say RA, reaction at A, reaction at C, acting at the center, meaning this RA plus RC is equals to 228 kilonewton. Therefore, RA, RC is equal to 114 kilonewton. So those are the forces at that point. Now we are concerned about the deformation in AB and AD. So we need the forces in those places, at that joint, right? We have a joint. So looking at joint A, if you have, this is A here, you have a force FAB, you have a force here FAD, so, right? Of course, then there's a force 114 kilonewton acting upwards, right? So this is joint A at the center here. Now we need to find the forces FAB, FAD. Now we have, if you look at this, we see that we have the we call it the Cartesian points, right? Coordinates, basically. So if you look at this point here, this is A, right? Come here, here. You can see here is 4 millimeters from A to D. Is that right? Yes. And then from B to D, we have 2.5 millimeters, and here we have 4.17 millimeters. Now, by geometry or by trig, basically, you can compare and use that to evaluate you can use that to determine the forces. So specifically, now, let's assume this is joint A and it's its own free body diagram, right? Now, I want to find the sum. So for us to find FAB and FAD, we need to, let's sum the forces, right? Because we have forces in the x direction and the y direction. basically, right? So sum of forces, let's start with sum of forces in the y direction, taking when it's facing up as positive, right? For this problem. So sum of forces is equal to 0. Now, FAD, right? If you, sorry, sorry, let's look at this. Now, sum of forces, okay, so just to mention, I know I just noticed I wrote this down without explaining this. So, if you're wondering how we came about this, it's just simply by Pythagoras theorem, right? 4 squared plus 2.5 squared, first squared that up, we get 4.714 meter, right? Okay. Now, sum of forces in the y direction, basically, right? If you look at this, we have this here. Of course, for this point in there has to be another equal force to counter it. That's what keeps it in equilibrium. Now, this is in the x-axis. It has no y component. Now, this is at an angle, but this force here has a y component, right? Now, we have to find that y component. So, but first of all, the 114 is pointing upwards, right? Then plus, if we plus this one, we need to find a component for this one too, right? So for the FAB y component, we need to find that one basically. So for us to do that, we can see now that we can use similarity, looking at both triangle. Looking at this and looking at that, right? This component, for us to find this the component for this part here, see, opposite of this, that's the opposite part, which is 2.5 over its hypotenuse, which is 4.717, multiplied by the force FAB, right? To give us that gives us the y component. Just like just to make things clear, FAB. Okay, sorry. Let me explain it this way. I think this should be better. So let's call here FAB the y component. This is the y, right? This is the x. FAB the x component, and here is FAB, right? Now, in trying to using similarity angles, basically. Now we know 2.5 over 4.717 is equal to FAB, the y component, over the resultant, right? So if you cross multiply, you get 2.5 FAB all over 4.717 equals to FABY. So that's how you find the y component. This, of course, is this here, this expression here, right? Now, of course, all of this is equal to 0. Okay, so if you compute FAB, you'll be getting minus 215.10 kilonewton, and that's FAB. Now, for this same drawing, your diagram here, we also have, this is the x direction, right? And for the x direction, we have this FAB. We also have an x component, FAB x, right? So to find the x parts too, let's use the same idea we had used here. We'll be getting 4 over 4.717 equals to FABX over FAB. Now, look at this. So it's 4, right? This is adjacent over the hypotenuse, right? Adjacent over the hypotenuse equals to this x over the resultant, which is this, right? That's how we get that. So now we have FAD. Okay, let me write things clearly. So sum of forces in the x direction, taking this to be positive, FAD. Now you may ask, what this is the FAD here. Look at it here, right? The FAD x direction, then the FAB, the y component, the x component of this. That's all we need for this. So FAD plus 4 over 4.717 FAB is equal to 0, right? That's what it is. Now we already have FAB. So we can substitute this here, right? When you substitute that here, we get a value for FAD without worrying of all the details. Before the 4 multiplied by minus 215.10 divided by 4.717 equals to 182.4 kilonewton, right? And that's FAD. Now to find the deformation, that's AB, and the other one is AD, right? Find the deformation. This is how we go about it. AB goes to FAB, the length AB all over the area of that member divided by E. E is universal for the beam. For the truss, sorry. So it's minus 125.10. I'm sorry. I have to convert the units times 10 to the power 3 multiplied by 4.717 divided by, that's 2400 times 10 to the power minus 6, 200 times 10 to the power 9. This is to ensure that the units will all be in meters, right? So delta AB minus 10 to the power 3. Negative because it's going to be it's negative, moving in the negative direction, right? So that's that. Similarly, delta AD will be FAD, LAD, AAD, and E. E is the same for both problems because it's the same material. From 4 times 10 to the power 3, that's the first one. We are using this in Newton, yes, kilonewton. So this multiplied by the length 4 divided by 1800 times 10 to the power minus 6 times E is 200 times 10 to the power 9 Pascal. To give you delta AD is equal to 2.03 times 10 to the power minus 3 meters. Delta. Yeah, so. Or you can still, it depends on you too, right? If you leave that in the AD millimeters, 2.03 millimeters. So that's how you find the deformation for a problem like this with a steel truss, basically. We're not given an angle, but again, you just use the idea of similarity or similarity. That way you isolate this point, this point here. There's a force here, there's a force here, right? Of course, you already have a force here. Now, once you have a force at an angle, know that it has y and x components. So now for the area of these members, we already have the values. So that's why we didn't use pi d squared over 4. We just simply use that. We're given the Young's modulus as well. And that's how we solved this problem. So one question people also want to ask is, if you have this right here, there's a force here, there's a force here, which has x and y components, the force here. What about this? Well, the answer, why we didn't use this, because this is what we call a zero force member, right? So a zero force member is a structural member in a truss that carries no force, right? There's no tension or no compression in it. So even though it's been applied here, there's no, you see how it, look at this force, this direction here. There's no force in this component. That's why it's not involved in our analysis, just here, here, and here. I hope this helps. You can watch the video and pause it to understand different sections. Thank you.